Hello, students, and welcome. So today, we're going to understand a very important topic from our Unit 10 Wave Optics, and that is diffraction. I know, it can feel a little tricky, but trust me, by the end of this short session, the whole idea will be completely crystal clear, super simple, and you'll be all set to get full marks in your exam.
Okay, so let's start with a question that seems to break all the rules we think we know about light. Since childhood, we've been taught that light travels in straight lines and it makes sharp shadows, right? But what if I told you that's not the whole story?
Just think about it for a moment. The middle of a razor blade is solid. It's opaque. It should block the light completely, shouldn't it? So how is it possible that a bright spot appears right in the middle of its shadow? No, this is not a trick question. It's a real thing that happens. And the answer, my friends, is diffraction.
So to really get this strange effect, we need to change our thinking a little bit. We have to stop imagining light as just a straight line, like an arrow. Instead, we have to see it for what it really is, a wave. And believe me, the moment you start thinking of it as a wave, everything just clicks. It becomes so much easier to understand.
And the best way to understand this is with a very simple analogy. Just imagine you're at the sea, okay? And you see water waves coming towards a small gap in a wall, like a harbor entrance. Now, do the waves just go straight through that gap? No, of course not. What do? They spread out. They bend out in circles on the other side. Well, guess what? Light does the exact same thing.
So let's just break this down step by step. First, you have these parallel water waves, these straight wave fronts coming towards that narrow opening. Now, the moment they reach that gap, something interesting happens. That little opening starts acting like a brand new source of waves. And then from this new source, the waves spread out in these nice circular patterns. And this bending and spreading of waves as they pass an obstacle, that is the whole idea of diffraction. Simple, right?
Okay, so the water wave analogy is fantastic for understanding the concept. But in the exam hall, you need the proper physics rule, the formula. So now let's look at the exact formula for this, the one that's going to get you those important marks.
And here it is. This is the condition for getting a dark spot, what we call minima or dark fringes. The formula is a sine theta equals n lambda. Now let's see what each part means. A is simply the width of the slit. Lambda, you know this, is the wavelength of the light we are using. N is just an integer, 1, 2, 3, and so on. And theta is the angle at which we see that dark spot. Make sure you write this down. It is very important.
So what is this formula actually telling us? In simple words, it's just a rule. Okay? It's a rule that tells us the exact angles where the light waves coming from different parts of that one single slit cancel each other out completely. And when waves cancel out perfectly, what do you get? You get a dark spot, a minimum. It's all about this cancellation.
But you might be wondering, how does this cancellation happen inside just one slit? It's a good question. So let's see how the whole pattern actually forms. We'll go through it step by step, and you'll see it's actually quite a clever idea.
So you remember Huygens' principle, right? We can imagine that the single slit is actually made up of countless tiny little light sources, all packed together. Now, just for a moment, let's pick two of them, one from the very top edge of the slit and one from the exact middle. As these two waves travel towards the screen, the one from the top has to travel a slightly longer path. Now, at a specific angle, this extra path distance becomes exactly half a wavelength. That's lambda over 2. And what happens when a crest meets a trough? They cancel out completely. And this doesn't just happen for these 2 points, it happens for every pair of points, one in the top half and its partner in the bottom half. And that's how we get our first dark fringe.
Okay, let's do a quick calculation to see this formula in action. The numbers are small, but the calculation is very easy, I promise. Imagine we have a laser with a wavelength of 650 nanometers. It shines on a tiny slit, just 50 micrometers wide, and the screen is 2 meters away. The question is, how wide will that central bright spot be? I really want you to pause here for a moment and try to calculate it yourself.
Okay, have you got the answer? It's 5.2 centimeters. Now just think about that for a second. Isn't that amazing? A tiny slit, just 50 micrometers. That's thinner than one of your hairs. Creates a bright spot on the screen that is more than 5 centimeters wide. That really shows you the power of diffraction. Okay, now for a very important section. Let's talk about the common mistakes, the silent killers in the exam. These are the small misunderstandings about diffraction where students often lose marks. So please pay close attention now. This here is the #1 mistake everyone makes. It feels wrong, but it's true.
Our common sense tells us if you make a hole smaller, the beam of light coming through should also get smaller, right? More focused. But in wave optics, the exact opposite happens. The narrower you make the slit, the more the light spreads out. It creates a wider pattern.
So you absolutely have to remember this. Just burn this into your mind. Narrow slit equals wide diffraction. Let's say it together. Narrow slit, wide diffraction. The smaller the opening, the bigger the spread. It might feel backwards, but this is a fundamental law of wave physics. Please don't forget this in the exam.
All right, so we've seen the main concept, we've looked at the formula, and we've talked about the big mistake to avoid. Now let's just take a step back and see how all this fits together, especially with interference. And then we'll do a quick summary for your final revision.
You know, a lot of students get confused between interference and diffraction, but the difference is actually very simple. Remember Young's double slit experiment? That was interference. That's what happens when waves from two or more separate sources mix together. But diffraction, well, diffraction is also a kind of interference, but it's the interference of all the tiny wavelets coming from within one single source, like all the points inside one slit. So both are about wave superposition. It's just the number and type of sources that's different.
So, for your exam, here are the key takeaways. First, what is diffraction? It's the bending of waves around an obstacle. Simple. Second, why does it happen? It's caused by the interference of light from within the same wavefront. Third, the most important formula for the dark fringes is A sine theta equals n lambda. Fourth, and please never forget this, a narrower slit produces a wider diffraction pattern. And finally, remember this is a real-world thing. Diffraction is what limits the resolution, the sharpness, of even the best telescopes and microscopes.
And before we finish, I want to leave you with one last question to think about. If light is always bending and spreading out, then why do the shadows we see every day look so sharp? I mean, think about your own shadow on a sunny day. It's so clear. It's not all fuzzy and spread out. Why is that? The hint is in the formula we learned today and the very, very small wavelength of visible light. Think about it. All the best for your exams.